Hi there and welcome. I will show you how the concentration works in coffee solubility in water, and this is my final project for transport process 2. Okay, the problem that we will talk about throughout the video is to know the behavior of the concentration of coffee at the bottom of a glass with water at a room temperature when adding 1 tablespoon of instant coffee, which is around 1.3 grams. We know that the measure of the glass are 6 centimeters of height and 2.5 centimeters of radius. Assumption are the diffusivity of the coffee is constant and is equal to this value. The solubility of the coffee is 2.17 grams per cubic centimeter, and the concentration must be estimated over time, a range of 60 seconds to 180 seconds. We assume on a steady state the initial concentration is equal to 0, there is no reaction and also no bulk motion. And this is the diagram of process, or small process of this problem. During daily activities, many unit operations can be identified and consequently the transport phenomena involved in each of them. It is worth mentioning that due to the simplicity of these activities, not all the factors involved in each operation are contemplated, not are complex calculation performed to describe the processes as an engineering will do or as will have to be performed in an industrial process. However, the design, control, and optimization is usually performed empirically. One of the unit operations that occur frequently in our daily life is solid-liquid extraction. In this operation, the predominant transfer phenomena is mass transfer and consists of solubilizing in a liquid component present in a solid. This happens when the solid comes into contact with the liquid, and the best known example is the preparation of coffee. The importance of this problem is because it is a quiet, simple, real-life example in mass transfer using some parameters like the diffusivity or the molar concentration in time. We can see it clearly how the topic functions. We can see how we did the problem, starting with the description of the Fick's law, having in mind the assumption made, and the resultant equations are the following. Then, after some steps using the error function and dimensionless parameter, we obtain the last equation, which is in terms of final concentration. After carrying out the corresponding calculation with the help of software, we arrive at the solution shown, where with the table of data obtained from the concentration, a graph was made to show the change in concentration with respect to time. In fact, we can observe by prediction and with the help of the graph that at some point the concentration will be the same no matter how much time passes. In conclusion, the results given in the report are understood to be correctly to apply in real life as well as intertwined with the theoretical part of mass transfer. The variables that we can be measured in this experiment, for example, could be the temperature of the water, since it is understood that as the temperature of the water increases, that solubility of the coffee increases, so the concentration at the bottom of the glass with water would reach its maximum in less time. Expressing these results makes me realize once again that many of the situation and industrial processes are only manifestation on a large scale of what happens before or eyes in daily life. So finally, this is the reference used for this project, and thank you for your attention.